3 foam cushions, a heater duct, a stowage decision made for comfort in an Arctic cabin. These are the components of a catastrophic system failure. On January 21, 1968, the collapse begins not with a weapon malfunction or an enemy engagement, but with cushions stowed too close to a heating duct on the lower deck of a Boeing B-52G Stratofortress. The consequence of this thermal ignition will not be measured in structural loss alone. It will be measured in the contamination of a fjord, the mobilization of an international recovery task force, and a race against the phase change of the Arctic Ocean. The objective is no longer a strategic patrol. The objective is to recover 4 thermonuclear weapons from a surface that is destined to dissolve. The aircraft is designated HOBO 28. It is operating under the command of the Strategic Air Command as part of Operation Chrome Dome. This is a continuous airborne alert profile designed to keep nuclear payload within striking distance of the Soviet Union 24 hours a day. The platform is a heavy bomber designed for high-altitude delivery, but today it is fighting a localized thermal crisis. The environment outside the hull is the definition of hostile. The location is North Star Bay, 7 miles west of Thule Air Base in Greenland. The ambient temperature is -75 degrees Fahrenheit, compounded by winds gusting to 80 knots. It is the height of the Arctic winter. There is no sunlight. The failure sequence initiates when a crew member places 3 urethane foam seat cushions against a heating duct manifold. The intent is to block a draft in the freezing cabin. The physics of the heating system, bleeding hot air from the engine compressors, turns the manifold into an ignition source. The foam ignites. The fire is fed by the forced air circulation of the environmental control system. Within minutes, the cabin fills with acrid, dense smoke. The electrical system, compromised by the heat, begins to shed load. The pilots lose instrument lighting. They lose radar. They lose stability augmentation. The aircraft commander assesses the trajectory. The fire is uncontained. The visibility in the cockpit is 0. The aircraft is effectively uncontrollable. The decision logic shifts from mission execution to immediate crew survival. The crew drives for the only fixed reference in the darkness, the lights of Thule, close enough that men on chutes can be found. Then the order to bail out is given. 6 crew members successfully eject or manually egress into the black void over the ice. The co-pilot, Leonard Svitenko, attempts to bail out through a lower hatch but sustains fatal trauma during the exit sequence. He is the sole casualty of the flight. The aircraft, now unmanned, enters a shallow spiral. It executes a sloppy 180-degree turn, ghosting back towards the landmass before losing lift. Gravity takes the airframe. The B-52 impacts the sea ice of North Star Bay at a speed of approximately 500 knots. The angle of incidence is shallow, approximately 20 degrees. This is not a crash that leaves a recognizable fuselage. The kinetic energy of the impact, combined with the structural breakup, shreds the aircraft into thousands of fragments. The fuel load ignites on contact. The explosion is not nuclear, but it is chemical and massive. The JP-4 aviation fuel creates a fireball that illuminates the polar night, scorching the surface of the frozen fjord. When the fire dies, it leaves a specific signature that becomes the primary reference point for the entire recovery operation. This is the concept of blackened ice. In a standard crash investigation on land, debris is mapped against terrain features like trees or elevation changes. On the sea ice, there are no permanent landmarks. The terrain is a featureless sheet of white. The impact creates a debris field roughly 1 mile wide and 3 miles long, defined visually by the soot and unburned fuel that stains the snow capability. This dark scar, the blackened ice, acts as the boundary marker. Inside that line, everything is both evidence and contamination. The soot is not just a visual marker, it is a carrier for the particulate matter generated by the destruction of the payload. The payload consists of 4 Mark 28 thermonuclear bombs. These are megaton-class weapons. They are designed to withstand the rigors of flight, but they are not designed to withstand a 500-knot impact into solid ice. The recovery teams arriving at Thule Air Base are not looking for intact weapons racked neatly in a fuselage section. They are looking for shattered components scattered across a darkened scar on a floating ice sheet. The operational constraint is absolute. The floor of the crime scene is frozen water. Core drilling showed the working ice could be as little as 2.5 to 3 feet thick, barely enough, and only if loads were controlled and constantly re-verified. But this stability is temporary. The Arctic season is a dynamic cycle. As the calendar moves toward spring, the temperature will rise, the ice will fracture, the structural integrity of the recovery platform will degrade. This creates a rigid time boundary known as the melt season. If the wreckage is not recovered before the melt, the ice will break apart and drift out to sea, or it will dissolve in place. In either scenario, the debris will sink. The depth of the water below the impact point ranges from 600 to 800 feet. If the heavy components of the nuclear weapons sink to the bottom of the fjord, they pass from a difficult surface recovery to a complex, perhaps impossible, underwater salvage operation. The environmental stakes are clear. The debris field contains radioactive material, fuel, and heavy metals. Allowing this mass to sink into the biosphere of the bay is not a permissible outcome. The mission parameters are set by the United States Air Force and the Danish government. The objective is complete remediation. The timeline is dictated by the sun. The recovery force must locate, identify, and remove the wreckage of HOBO 28 and its 4 nuclear weapons. They must do this in total darkness, in temperatures that freeze hydraulic fluid and shatter steel, on a surface that is slowly moving toward the open sea. The fire that brought the plane down has extinguished itself, but the heat of the nuclear cores remains and the ice is not permanent. When 4 thermonuclear weapons impact a solid surface at 500 knots, the immediate fear is a nuclear yield. Here, that fear centers on the 4 Mark 28s already scattered across the ice. Yet, on the ice of North Star Bay, the horizon remained dark. There was no thermal flash, there was no mushroom cloud. The absence of a nuclear detonation is not a matter of luck, it is a matter of physics and precise engineering design. The mechanism that governs this outcome is known as hydrodynamic disassembly. A nuclear weapon is a precision device. To initiate a nuclear yield, the conventional high explosives surrounding the radioactive core must detonate with perfect simultaneity. This simultaneous compression drives the plutonium pit inward, increasing its density until it reaches a critical mass. In the chaos of a high-speed crash, this symmetry is impossible to achieve. The impact shockwave triggers the conventional explosives, but they fire randomly or asymmetrically. Instead of compressing the core into a critical mass, the explosion acts outward. It shatters the plutonium pit. It pulverizes the uranium tamper. The weapon does not go nuclear. It disassembles itself violently. The result is not a nuclear explosion, but it is a massive conventional detonation. This transforms the event from a strategic catastrophe into a radiological environmental disaster. The physics of the crash converted the weapons into what is effectively a dirty bomb. The force of the conventional explosives shattered the radioactive metals into microscopic dust. This dust was then caught in the updraft of the burning aviation fuel. The plume of the fire acted as a distribution system, lifting the pulverized plutonium, uranium, and tritium high into the Arctic air before depositing it back onto the snow. The recovery team now faces a hazard that is invisible. The primary contaminant is plutonium-239. This material is an alpha emitter. In the hierarchy of radiation, alpha particles are heavy and carry high energy, but they have very low penetrating power. An alpha particle cannot penetrate a sheet of paper. It cannot penetrate the flight gear of a pilot. As long as the material remains outside the body, the risk is manageable. The danger profile changes instantly if the material is internalized. If the dust is inhaled into the lungs or ingested, the alpha particles bombard the surrounding tissue directly. The toxicity is extreme. The cleanup crews are not fighting a radiation field that burns them from a distance. They are fighting a dust that kills if they breathe it. Detecting this dust in the frozen darkness requires specialized instrumentation. Standard Geiger counters are often insufficient for detecting the low-energy gamma rays that accompany the alpha decay of plutonium in this specific environment. The solution is a probe designated the Fiddler, or field instrument for the detection of low-energy radiation. This device is a scintillation counter designed to detect the faint signature of americium-241, a daughter product that exists within the weapons-grade plutonium. However, the instrument was designed for standard operating temperatures, not the high Arctic. In the -75-degree cold of Greenland, the batteries fail. The crystals in the sensors can crack or drift in sensitivity. To make the Fiedler probes functional, technicians must improvise thermal insulation, wrapping the delicate electronics in supplemental heat shields and keeping battery packs inside their parkas until the moment of use. The intersection of these mechanics creates the operational reality. The weapons have undergone hydrodynamic disassembly. The core materials are now spread across the blackened ice in a fine particulate layer. The survey teams must walk the grid with their modified Fiedler probes, mapping the invisible fallout zone. Every step kicks up snow. Every gust of wind potentially redistributes the alpha emitters. The contamination is currently trapped in the snowpack, sitting on top of the ice. But the ice is a moving conveyor belt, and beneath it lies the deep water of the fjord. The radiation is contained only by the temperature, and the temperature is rising 3 feet. That is the thin margin standing between the recovery teams and the black water below. Core drilling established a surface that could take loads only under strict discipline and constant re-verification. To the engineers moving heavy equipment, the ice is not land. It is a floating plate with a calculated breaking point. The operation is defined by a critical engineering variable known as ice load bearing. This concept dictates every movement on the surface. Arctic specialist Core drilled the ice, set a hard load limit for heavy gear, and even computed the date when operations had to stop before breakup. Ice load bearing is not a fixed number. It is a dynamic relationship between the thickness of the ice, the temperature of the air, and the distribution of the weight placed upon it. A concentrated load, like the tires of a heavy grader, exerts more stress than a distributed load, like a sled on runners. If the load exceeds the bearing capacity, the result is not a slow leak, it is a catastrophic fracture. The ice snaps and the equipment vanishes into the black water below. The engineers must constantly drill core samples to verify the thickness, calculating the safety margin for every vehicle that leaves the shore. The environment tests these margins immediately. The temperature remains deep below zero. In these conditions, the mechanical reliability of standard military hardware evaporates. Hydraulic lines freeze, diesel fuel gels in the tanks. Batteries lose their charge in minutes. The United States Air Force possesses the most advanced aviation technology on the planet, yet on the surface of the bay, their logistical chain is breaking down. The trucks and tracked vehicles designed for temperate zones struggle to start, and when they do start, they risk cracking the very surface they traverse. To solve the mobility crisis, the operation turns to a logistical solution that predates the internal combustion engine. They hire the local Inuit hunters. The locals possess the only transport technology proven to function reliably in the high Arctic winter, the dog sled. This is a decision of pure utility. The integration of Inuit sled teams into a classified nuclear recovery operation is not a gesture of goodwill. It is a requirement for access. The dogs do not require hydraulic fluid. They do not require battery warmers. They require fuel in the form of protein. To sustain this biological transport network, the Air Force Logistics Command begins flying in massive quantities of horse meat. Over 1,500 pounds of meat are delivered to feed the sled teams. The economy of the recovery effort shifts. The pilots fly the strategic assets, but the dog teams provide the tactical mobility required to cross the ice without fracturing the load limits. With the transportation network established, the survey teams begin the process of bounding the site. They are not searching for a needle in a haystack. They are searching for microscopic dust on a shifting glacier. The visible soot of the blackened ice provides the initial target, but the contamination has spread beyond the visual scar. The wind has carried the alpha particles outward. To define the true perimeter, the teams establish a rigid survey grid. They drive wooden stakes into the ice, creating a coordinate system in the darkness. Portable floodlights, powered by generators struggling against the cold, cast long shadows across the snow. The survey technicians, transported by the dog sleds, move from stake to stake. They hold the Fiedler probes inches above the surface, listening for the electronic click that indicates the presence of plutonium. They are building a map of invisible hazards. This mapping process reveals the scope of the problem. The debris is not sitting neatly on the surface. The heavy impact has driven wreckage deep into the snowpack, and in some cases, into the ice itself. Fine contamination has settled into the snow's texture and frozen into the crust. The grid now has to answer two questions at once: where the signal is and how deep it has penetrated. The footprint is widespread, extending well beyond the initial impact scar. The ice load bearing calculations hold for now, but the clock is ticking. Every day the sun gets closer to the horizon, the temperature inches upward. The 9-foot buffer is the only thing keeping the radioactive waste out of the ecosystem, and that buffer is temporary. The grid is defined, the transportation is solved. The next step is the physical removal of the hazard. Finding the debris is one problem. Moving thousands of tons of it before the water rises is another. The operational objective has shifted from survey to extraction. The survey teams have defined the boundaries of the radioactive footprint. The physics of the situation are now dictated by a simple phase change. The contaminated snow and ice are stable only as long as they remain frozen. Once the ambient temperature rises, the snow will become water and the containment will fail. The plutonium will migrate from the surface of the ice sheet into the water column of the fjord. To prevent this environmental release, the Air Force must execute a removal operation that rivals a large-scale mining project. They must harvest the surface of the frozen sea. The technique selected for this extraction is borrowed from agriculture. It is a process known as windrowing. In a farming context, windrowing involves raking hay or grain into long, continuous rows to dry before baling. On the sea ice of North Star Bay, the harvest is radioactive snow. Heavy road graders, brought in by airlift, scrape the top layer of the ice sheet. They do not cut randomly. They work in disciplined parallel lines, pushing the blackened, contaminated snow into long, precise ridges. This method serves a dual purpose. First, it concentrates the low-density snow into high-density piles, making the subsequent loading process more efficient. Second, it provides a visual control system. The operators can see exactly where they have cut and where the contamination remains. The graders strip the surface down to the hard blue ice beneath, effectively peeling the radioactive skin off the fjord. The result is a landscape of clean ice separated by long, dark windrows of toxic debris waiting for collection. The collection phase introduces a volume constraint. The material cannot simply be moved to the shore and piled up. If the snow melts on the shoreline, the runoff will carry the plutonium directly back into the ocean. The containment must be absolute. The solution is the deployment of heavy industrial storage units. The recovery task force utilizes massive steel tanks, each with a capacity of 25,000 gallons. These are not standard shipping containers. They are liquid, tight vessels designed to hold the snow as it melts and turns into radioactive sludge. This creates a logistical architecture known as the tank farm. The tanks are too heavy to be filled on the ice and then moved while full. The risk of breaking through the ice load limit is too high. Instead, the empty tanks are positioned on a staging area on the shoreline, a secure zone on solid ground designated as the tank farm. The windrowed snow is loaded onto sleds and trucks out on the ice, transported across the frozen bridge to the shore, and then transferred into the waiting tanks. The scale of this transfer is industrial. The crews are not just sweeping up dust, they are moving a geological feature. By the end of the operation, the removal teams will excavate and transport approximately 237,000 cubic feet of contaminated material. This volume represents the top layer of the crash site, scraped away inch by inch in the darkness. As the tanks fill, they are sealed and tagged. The tank farm becomes a holding pen for the wreckage of the weapon cores. These 25,000-gallon coffins are not the final destination. They are a buffer, holding the waste until the summer shipping season opens the sea lanes. Eventually, ships like the USNS Marine Fiddler will arrive to transport the tanks back to the United States for final processing at the Savannah River plant. The procedure is a race against the calendar. The graders and loaders work around the clock under artificial lights. The windrows shrink as the trucks haul the material away. Slowly, the dark scar on the ice begins to fade. The graders scrape until the surface is white again. The immediate radiological threat to the surface environment is being neutralized, cubic foot by cubic foot. However, the removal of the snow solves only the environmental problem. It does not solve the accounting problem. The debris recovery teams are counting the shattered components of the 4 bombs. They are matching serial numbers and weighing fragments. For 3 of the weapons, the recovery is substantial. The parts are mangled, but they are present. But as the snow is cleared and the ice is scrubbed down to the base layer, a discrepancy emerges in the inventory. The surface is clean, but the count of recovered weapon parts remains incomplete. There is a gap in the evidence that windrowing cannot fix. The calendar turns, the sun rises higher. The inevitable phase change occurs. By August 1968, the solid operating surface of the winter has disintegrated. The 9-foot thick ice sheet is gone, replaced by the open, dark water of North Star Bay. The surface recovery operation is complete. The tanks are filled, the windrows are gone, and the graders have been airlifted out. By all standard metrics, the remediation is a success. But the forensic accounting tells a different story. The inventory of recovered components shows a specific critical gap. The secondary stage of one thermonuclear weapon is missing. The physics of the impact reconstruction suggests a vertical trajectory. While the explosion scattered most of the debris horizontally across the ice, a heavy, dense component, the uranium cylinder that forms the secondary stage of the weapon, possessed enough kinetic energy to punch directly through the ice sheet at the moment of impact. It did not stay on the surface. It traveled to the bottom of the fjord. The mission pivots from environmental cleanup to deep water salvage. The tool for this environment is not a dog sled or a grader, it is the Star 3. This is a small, 2-man submersible brought to Greenland specifically to hunt for the missing cylinder. The transition to underwater operations changes the constraints entirely. On the ice, the limitation was temperature. In the water, the limitation is energy and visibility. The Star 3 is not a nuclear-powered endurance vessel. It is a battery-operated probe on a short tether. Its operational window is defined by lead-acid battery capacity. The submersible can operate for less than 12 hours before it must surface and recharge. This creates a stop-start rhythm to the search. The pilots cannot loiter. They must dive, search, and return, managing their AMPI hours as carefully as their oxygen. To find a single cylinder in a vast, silt-covered bay, the team employs a technique known as survey grid saturation. In a standard search, a vessel might run parallel lines with wide spacing to cover ground quickly. In a saturation search, the spacing is compressed. The goal is not speed, it is coverage. The submersible and its surface support ship run overlapping transects, ensuring that every square foot of the sea floor is scanned by sonar or viewed directly through the viewport. There can be no gaps between the lanes. The sensors paint a picture of the bottom that is cluttered and chaotic. The floor of the bay is scarred by the impact. There is debris, twisted metal, and the natural unevenness of the fjord bed. The Star 3 navigates through this cold, dark topography, fighting the turbidity of the water. The silt at the bottom is easily disturbed. A single thruster movement can cloud the visibility, blinding the pilots and rendering the visual search useless until the sediment settles. For weeks, the submersible combs the grid. They locate debris. They locate parts of the aircraft structure. They map the final resting place of the impact fragments that escaped the surface cleanup. But the specific target, the intact secondary stage, remains elusive. The sonar returns are ambiguous. The visual identification is hampered by the silt burial. The heavy uranium component has likely buried itself deep into the soft mud of the sea floor, hiding from the sensors. The operation reaches a decision point. The search has saturated the grid. The reliable signals have been investigated. The operational window for open water is closing. The Arctic winter is returning, and the ice will soon reclaim the bay. The command authority is faced with a trade-off. They can continue a diminishing return search for a buried component, risking the submersible and the crew as the weather turns, or they can assess the environmental risk of leaving it in place. The engineering assessment concludes that the cylinder, buried in the silt, poses a minimal risk to the food chain. It is chemically stable. It is isolated. The recovery of the surface contamination has removed the primary biological hazard. The cost of further pursuit outweighs the potential gain. The decision is made, the Star 3 is recovered, the search for the cylinder is halted. The outcome path is set. It is not a total failure, nor is it a total recovery. It is a calculated partial success. The surface is clean, but the fjord will keep a part of the payload forever, 93%. This is the final number entered into the ledger of Operation Crested Ice. It is a percentage that represents both a staggering industrial achievement and a permanent, lingering uncertainty. After months of scraping the ice, filling the tanks, and shipping the frozen waste to the Savannah River plant, the United States Air Force and Danish scientists concluded that 93% of the plutonium released by the impact of HOBO 28 had been recovered. The operation had successfully removed the vast majority of the alpha-emitting dust from the biosphere. The surface of North Star Bay was visually clean. The water samples remained within acceptable limits. By the standards of crisis management in 1968, the mission was declared a success. But the cost of this percentage cannot be measured solely in curies or cubic feet of snow. It is measured in the operational limits of the Strategic Air Command. The crash at Thule was not an isolated misfortune. It was the breaking point of a system that pushed men and machines beyond sustainable boundaries. The legacy of the crash is found in the details of the missions that preceded it. The crews flying Operation Chrome Dome were subjected to 24-hour airborne alert profiles in conditions that defied human physiology. The investigation into the program revealed the depth of this strain. It was not just the fatigue or the engine maintenance. It was the microscopic indignities of the Arctic environment. Survival reports from the era documented logistical failures as specific as urine collection bags, freezing solid inside the flight suits of the pilots. The environment was so hostile that even the most basic biological functions became a hazard to safety. The B-52 was a weapon of war, but in the high Arctic, the cold was the primary adversary. The crash of HOBO 28 proved that the risk of keeping nuclear weapons airborne 24 hours a day outweighed the strategic advantage. The accident at Thule marked the end of the airborne alert program. The bombers were grounded. The strategy shifted. The era of Chrome Dome was over. The site itself remains a subject of scientific vigilance. The decision to leave the missing secondary stage on the ocean floor was a calculated trade-off, but it required a commitment to long-term observation. The debris field is not forgotten. It is monitored. In the years following the crash, expeditions returned to the fjord. Danish investigations, particularly those led by the Riso National Laboratory, conducted extensive surveys of the sediment, the water, and the marine life. They were looking for the migration of the remaining 7%. The data from these longitudinal studies confirmed the engineering hypothesis made in 1968. The plutonium that escaped recovery has largely settled into the deep sediment. It is heavy. It does not dissolve easily in seawater. It has not moved up the food chain in significant concentrations. The silt of the fjord acts as a natural containment vessel, burying the last remnants of the weapon in a geological tomb. The missing cylinder, the piece that punched through the ice and evaded the Star 3, sits somewhere in that darkness, chemically stable and physically isolated. Operation Crested Ice ends as a managed outcome, not a clean recovery. It was never going to return 4 intact weapons to Iraq. It was built to prevent a permanent release into the bay. Instead, the operation was a massive exercise in damage control. It demonstrated the ability of an industrial force to project power into the most inhospitable environment on Earth and execute a complex remediation plan. They beat the melt season. They mobilized a logistics chain of ships, aircraft, dog sleds, and submersibles to erase a radioactive scar before the ice turned to water. Today, North Star Bay looks much as it did before the morning of January 21, 1968. The sea ice forms and breaks with the season. The darkness of the winter gives way to the light of the summer. The surface is white and pristine. There are no black windrows of contaminated snow. There are no yellow tanks waiting on the shore. But the chart of the bay still carries the invisible annotation of the event. The 7% remains. The crash of HOBO 28 proved that while the Air Force could master the logistics of recovery, they could not negotiate with the laws of physics. The energy of the impact dispersed the core, and the depth of the fjord claimed its share. The operation proved that you can clean the ice, but you cannot undo the fall.